Alright, so today we're looking at AP Stats from the 2019 exam, question number 3. A medical researcher surveyed a large group of men and women about whether they take medicine as prescribed. The responses were categorized as never, sometimes, or always. The relative frequency of each category is shown in the table. Part A. One person from those surveyed will be selected at random. What is the probability that this person selected will be someone whose response is never and who is a woman? Okay. This is simple. It's grab my pen. So part A, the probability of never and woman. Well, probability of never is 0.12. The probability of woman is 0.53. So and means multiplication. So 0.12 times 0.53 is equal to 0.0636. Now, a quick shortcut is that this number right here is always this event here multiplied by this event here. So if you just realize that this question is an and you can multiply it, go ahead. But you can also realize that this is just simply the answer. The probability of woman and never is right here on your two-way table. So there you go, part A, and then just make sure you do this. And W. And you should indicate somewhere what N means, what W means. Okay, part A, that's part A1, part A2. What is the probability that the person selected will be someone whose response is never or is a woman? Okay, well, we don't know if they are mutually exclusive events. So we're just going to use the standard OR formula. So the probability of woman or never is equal to the probability of woman plus the probability of never minus the probability of woman and never. So the probability of woman is 0.53. The probability of never is 0.12. And this value is right up here, 0.0636. Let's go to calculator. 0.53 plus 0.12 minus 0.0636 is going to equal 0.5864. Damn it. Woman or never. Okay. Now time for A3. Here we go. What is the probability that the person selected will be someone whose response is never, given that the person is a woman? So here is the basic formula. The probability of never given woman is equal to the probability of never and woman divided by the probability of woman. Okay, let's go to our calculator. We know that the probability of never and woman is 0.0636. We know the probability of woman is 0.53. That means the answer is just 0.12. There you go. Remember, so this means N and W or A and B divided by B. Okay. Now let's move on to the next part. For the people surveyed, are the events of being a person whose response is never and being a woman independent? Justify your answer. Okay. Well, I mean, there's multiple like independence formulas. One of them that I know is uh, if probability of A is equal to the probability of A given B, and the probability of B is equal to the probability of B given A, the events are independent. So we'll do this question two ways. We'll first do it like this, and then there's another way. So if we say A is woman, that means you already is woman given never, never, never given woman. Okay, so now for woman is 0.53. So is 0.53 equal to, let's see, woman and never is 0.0636. 6 and never is 0.12. Yep. So this fraction is 0.53. Okay, so that's first part of the formula done. Now let's check the second part. So probability of never equal to probability of never given woman. Well, never is this 0.12. We know that N and women is 0.0636, and we know that woman is 0.53, and yes, this works out to 0.12. So now you can say because the probability of woman is equal to the probability of woman given never, and the probability of never is equal to the probability of never given woman, the two events are independent. Now another way to go about doing this is, let's reread the question. It says, are the events of being a person whose response is never and being a woman independent? So this was a little suspicious because simply just person could mean men and women. So now I'm thinking, what if we do this? What if we state P never? We know this to be 0.12. So let's find the probability that it's woman given never and the probability that it's man given never. And let's see if these are equal to 0.12, then we are good. Sorry, not woman or man given never. It's never given the gender. Because the question says, are the events of being a person whose response is never and being a woman independent? Okay. Yeah. So never given woman and never given man. So this is and a woman divided by woman. And if these values are equal to 0.12, then we're good. So n and woman is 0.0636. Woman we know is to be 0.53, and yes, this is 0.12. We're good. Now let's check man. 0.0564. Man, 0.47. Again, I'm just using the here. You know what? Let me do another thing. I'm gonna make a two-way table quickly. I'm gonna call this A, complement of A, B, complement of B. Okay. Here we go. So this is equal to the probability of A and B. This is A and B complement. This is A complement and B. This is A complement and B complement. Okay, and then your total these are all your total probabilities. So these are basically your conditional probability, and there's another term. Let me find it quickly. Conditional and there's another term. I'm trying to find it. Hold on. Okay. Um, it's a term I can't remember, but all I know is that the inside these are conditional probabilities, and then there's another term on the outside. I'll try to find it and put it in the video description. So this is equal to, let's see, 0.0564, 0.1 divided by 0.47 is going to equal 0.12. So now we can simply state. So before, up here, you would have said, since P woman is equal to P woman given never, and P never is equal to P never given woman, the two events are indeed independent. So now down here, these are basically just two different ways of just confirming the events are independent. So now down here, all you would have to say is, um, yes, they are independent. Because gender does not change the probability that their response is never. Because the three calculated probabilities are equal. And now up here, I'll just write it. So in case you found this method simpler, you can say because woman given never and the events W and N, quote unquote W and quote unquote N, are independent. And remember, up here you should always say so on and so forth. Like, you should always define your variables so they know what you're doing. Okay, now part C. Assume that in a large population, the probability that a person will always take medicine as prescribed is 0.54. If 5 people are selected at random from the population, what is the probability that at least 4 of the people selected will always take medicine as prescribed? Okay, so this sounds like a binomial distribution since they're talking about a large population. So that's like one of the conditions for bins. Um, the probability that okay, if 5 people are selected at random from the population, what is the probability that at least 4 of the people selected will take the medicine as prescribed? So we can write that as this. You know that this is we have to use binomial CDF because this is, we're not finding an exact probability. So we're finding the probability that X is at least 4. Let me check. Yes, X is at least, and at least is denoted as greater than or equal to 4. Um, well, if we did binomial, like for example, if we go to our on second vars binomial PDF, we know we're doing 5 trials. The probability of success is 0.54. X value is 4. We paste. Yeah, no, that that's not correct because how do I describe this? Okay, you know what? How will we write this as 1 minus x less than or equal to 3. Um, and if we do second math, or no, math probability, go over to NCR, 5 choose, let's see, I guess 3 now. Nope, that isn't working either. Now let me try it. I'm using the NCR function to try to see if there's a simpler way, like if there's a way to show viable work. Um, no, that doesn't work. Let's try 2. Okay, I think what you could do then, you just you'd have to just do this binomial CDF. Um, you have to first state x as a random variable. Um, x is the number of people who always take medicine. Right, so if you're finding an exact probability, yeah, NCR wouldn't work here because you're not finding an exact probability. You're finding less than or equal to, greater than or equal to, and here we're using greater than or equal to. So you can't really use it. I mean, you could use NCR here, but I think that's too much. So you have to define binomial CDF. Your n is equal to 5. Your p is equal to 0.0, or not 0.0, just 0.54. And you also have to state your x to be equal to 3 because we're finding 1 minus the probability of x is less than or equal to 3 is equal to the probability that x is greater than or equal to 4. So it would be 1 minus binom 5, or binom CDF 5.54, 3, 1 minus, okay, second vars binomial CDF, 5 trials, 0.54, 3, and then that's equal to 0.7585, and then 1 minus that is equal to 0.2415. So you might be wondering, like, why did you have to do 1 minus? It's because, okay, let me draw a curve quickly. So here's this, right? We're trying to find probability that x is greater than or equal to 4, right? So here's our mean. We're trying to find that it's this, right? But all the calculator functions are in the opposite. Our calculators function like this. So if we typed in, like, it doesn't recognize greater than or equal to. It just works in the less than or equal to. So if we want to find this region of the calculator, we just know that it's the opposite of x is greater than or equal to 4. That means it would just be probability that x is less than or equal to 3. And then if we want this probability is for this shaded area. So if we wanted to again find this shaded area, it'd just be 1 minus this. That's why you have to change it to less than or equal to, and then 1 minus that, because the calculator doesn't deal with greater than values. It deals with less than. So there you go. This should be accurate solutions to the third question from the 2019 exam. Thanks.